Okay, so we can continue with our lecture. What we already learned last Tuesday, it was related to the neural network, and we learned about the layers in the neural network. We have three kind of layers: the input layer, the hidden layer, and the output layer. And the hidden layer can be anything. You can define many layers, but the input layer is about the variable that you can use for the training, and the output layer is the result or the output or the target that you want to get. So you know about the forward and the backward propagation. And the learning phase, during the learning phase, the network learns by adjusting the weight. So you already know the mechanism of the back propagation, how it can update the weights. So the weights will be updated until you can get the minimum errors. We have the loss function. So if the loss function or the error is minimum, then the training stops. The backpropagation algorithm is the most common learning method and has been successfully applied to a variety of learning tests. So what you already learned is the very basic neural network, and it has been applied to many domains. If you go to orange, let's say I'm just using the iris, you can see the neural network. So there is a neural network here, but this is a very basic neural network. So you can see that there's a definition about the number of neurons in the hidden layers. It means we need to define how many units in the hidden layer. And this units, it is only in one layer, in one hidden layer. And then this is the activation function, the identity, logistics. So logistics is the same with the sigmoid, sun, and ReLU. So if you look at the previous PowerPoint, so we call this is sigmoid or logistics. Sigmoid or logistic activation function. And you can get it also in this activation. I think now many of the networks use ReLU. So this is the rectifier linear unit. This has been applied also in many domains. Solver. So nowadays also there are many people who develop the solver, but the most optimized people use Adam optimizer. The regularization, so the alpha, it means the learning rate, and we can define how big is the learning rate. So usually, people will use a very small value of the learning rate, and this is the maximum number of iteration. So you already know about the maximum iteration in our definition about the neural network. The idea is just to set the parameters, and you can check the test score. If you cannot see the result, it is because you need to connect the test and score with the data. Then you can see that based on the cross-validation approach, we can get 94.7 accuracy. So this is the basic neural network. If you want to improve with the deep neural network, you need to code by yourself in Python. Or if you want to connect with Python code, you can have the Python script. So in the Python script, you can continue, okay, what you already know in the Jupyter notebook, and then you can make the script here. For example, now we are doing the import. We are going to import the NumPy, and then we need to call for every of the data in the orange. And after we have those data, what you are going to do. So if you run this script, this one there is no such result. If you want to print, see, maybe it's not, like this one. I'm going to print the out data. Then the out data will print the domain and the ARR. ARR is the array. If I just print out the out data, then it will print only the ARR, which is this array. So this array is shown in this result. So you can deal with many Python scripts. If you want to develop your neural network here, that's also possible. But of course, you need to consider your computer specification. Maybe if your computer is not good enough, it will take a long time to train the neural network. Okay, that's about the neural network. So I'm going to continue with the new chapter. So the new chapter is about the alternative of clustering. So you already learned many things. Hopefully from the assignment, you can get more ideas how to apply what we already learned until now. The association, the classification, clustering. And now I'm going to teach you a new methods in the clustering. At the first part of clustering, you already learned about partitioning. You already learned about hierarchical methods. So in this chapter, we are going to learn about density-based and grid-based methods. And we are going to look at some evaluation of clustering. So clustering, it means you want to group, you want to check the similarity of the data. But the problem in the k-means, if you still remember, one of the problem is the non-convex shape. Non-convex shape. You still remember? We can just make cluster something like a convex shape. But if there is a data something like this one, we cannot make a good cluster. The density-based clustering method, it means we want to see the density. Density, it means we want to check the local cluster criterion. We call it the density connected points. So the major features, we want to discover clusters of arbitrary shape. The arbitrary means any shape, every shape. So you can get the, we call it the moon shape, like this one. Or maybe you can get some clusters like triangle shape. So in any shape, as long as we have the density, then we can discover it. And it can handle noise. it is one scan. One scan means it is not repeatable. So if you do one flow, then yeah, this is only one time scan. And then we need to have some parameters. We call it the density parameters. It is to terminate the condition. So we call this is the termination condition. There are some studies. Yeah, DBSCAN is the earliest part. There are some other studies like optics, then clue, click. So we will check what is the meaning by click in the grid-based method. The density-based clustering, we will use two parameters. The first parameter, we call it EPS. EPS, maybe we can say like the epicentrum. It is the maximum radius of the neighborhood. Let's say, yeah, I have this circle, and we have the EPS, which is 1 centimeter. So from this center, yeah, we want to check the 1 centimeter in the boundaries. So from this, let's say this is the center. So I want to check the 1 centimeter in the boundaries. And then we have minimum points, mean PTS. It is the minimum number of points in an EPS neighborhood of that point. So let's say if I have this EPS, so the minimum point, if I set into 5, then I need to have at least 5 points, at least 5 data. So 1, 2, 3, 4, 5. If there are 5, then okay, I can say that it is one cluster. So we call this is the NEPS. N means the numbers. So we have the Q and we have the P. We have the P, we have Q. So Q belongs to D such that this is like condition. Distance between P and Q is less than the EPS. So if we know that this is 1 centimeter, so if the distance between the object P and the object Q is less than the EPS, then the Q will belong to the cluster. So it means we want to know all the Q that is belong in the EPSP. We can say it is directly density reachable. Directly density reachable. If a point P, it is reachable from a point Q. And we have the EPS, we have the min PDS. If the P belongs to the NEPSQ, so the NEPSQ is this one. And we will have another condition, we call it core points. The core points mean the number of data that fits with this condition is higher than the minimum PDS. So the easy way to say about this condition is, for this one, if the distance is lower than 1 centimeter, then it is directly density reachable. The core point condition, it means if there are at least 5 points in the 1 centimeter, then it is directly density visible. Okay. So these two conditions. If the distance is 1 centimeter and if there are 5 points in 1 centimeter, we call this is directly density visible. So there are another concept, we call it density connected. So in the previous one, we say the density reachable. It is the density reachable, or point P is density reachable from a point Q with regard to, okay, WRT means with regard to EPS. You know the EPS is the distance, and then the minimum PTS, which is the minimum points, if there is a chain of points, a chain. So there is a Q, and then we know that there is a P, and then we have the this one P1. There is a Q, and then we know there is a P1, which is in the density, and then there is another P. So if we have this one, the P1 is still in this density reachable, and then the P, it is still in this minimum points and it is still in the EPS, then we call, the P is density reachable from Q. Okay. Even though we can say that it is still far. However, we have the chain of points. It means the Q is the density reachable to P1, and the P1 is density reachable to P. So we call the Q is density reachable to P. And we have another concept, we call it density connected. A point P is density connected to a point Q with regard to EPS and minimum points if there is a point O, there's a point O here, such that both P and Q are density reachable from O. So in this case, we want to look the perspective from O. Okay. O is density reachable to P, and then O is density reachable to Q. Then the point P and the point Q is density connected. Okay, then that's the definition. So let's see one algorithm. We call it the density-based spatial clustering of applications with noise. In short, we call it DBSCAN. So DB means density-based. S is the spatial. Spatial is like the space. Okay. Clustering of application, okay, with noise. N is the noise. It relies on the density-based notion of cluster. We want to check the density. So a cluster is defined as the maximal set of density connected points. What is the density connected points? We got from this, okay, density connected. We need to discover clusters of arbitrary shape in the spatial database with noise. So later on, we will have three kind of concept. We call it core. Okay? This is the core points. The core points, if it fits with this requirement. In the EPS 1 centimeter, we have the 5 points. So if it is the core, so in the boundary of 1 centimeter, we have 5 points. 1, 2, 3, 4, 5. We call it border points. When we say it is border point, in this point with the boundary 1 centimeter, we have less than 5. It is less than 5. So we have only 1. The other point is the outlier point. The outlier point means it is only 1 or that point itself. So we call this is outlier. Okay, so we have three kind of point: core, border, and outlier point. So the algorithm is something like this one. We need to select the point P, and we need to retrieve all points density reachable from P. We have the EPS, we have the min PTS, and then we need to check if P is a core point. What is core point? The core point is a point that in the surrounded area have at least 5 points. Then if it is a core point, the cluster is formed. If P is a border point, no points are density reachable from P, and DBSCAN visits the next point of the database. Continue the process until all the points have been processed. So what we want to find is the core point. Let's see from one example. Now we have 13 points. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So based on the data, you have 13 points, and let's set the EPS is 0.6. And then let's set the minimum points is 4. So determine the cluster results and the outlier. So the cluster results means I need to define the core point and the border point. Okay. So at the end, we will check this one as the core point. So this point is the core point because we have 1, 2, 3, 4, 5. So this point is a border point because we have only 1. This point is outlier because we have only its point. So let's check how we can get this one. First, you need to calculate the distance. I think you know how to calculate the distance. Here we have the x equals to 1, y equals to 2. Okay. Now let's start from the first point. From the first point, the distance, okay, the distance from one point to this one, of course, it is 0. What about this? If we use the Euclidean distance, so we have the 1 minus 3 power of 2 plus 2 minus 4 power of 2 and 2 power of 2 plus 2 power of 2. Okay. We have the square root. So we have the square root of this one. So the square root of 8. Okay. The square root of 8 is 2 point something something. 2 maybe 2.8. So the result is this one. This is the distance. What about the distance of this? Yeah, we can do with the Euclidean distance again, and we get the result. The distance is this one. What about this distance? Yeah, the same. And these all are distance from the point 1, 2. Okay. So we will check what is the EPS. The EPS is the neighborhood or the density that the distance should be less than or equal to 0.6. So is it 0.6? No, 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 no. Okay, this one. This one is lower than 0.6. This is no, no. Okay, this one. It is lower than 0.6. This one no, no. Okay, then we have 2 points that is in the EPS 0.6. So in the perspective of 1.2, we have 2 points which is the neighborhood points, which is 1, 2, 2.5, and the other is 1, 2.5. So those 2 points are having the EPS less than 0.6. Now the question is, how many points do we require? Based on this one, we need to have 4. But using this EPS, we have only 2. Okay, so let's keep it like this. We can go to the next point. So we go to the next point, 3, 4. You can calculate the distance. Okay. You can calculate the distance from 3, 4 to 1, 2, 3, 4 to this point, 3, 4 to this point, 3, 4 to this point, and so on. And then again, you will check which point have the distance lower than 0.6. If you calculate, the 3, 4 will have the neighborhood point 2, 5 and 4, and we have 2,8 point 2.8, 4.5. So again, we have 2 points. Okay, we have only 2 points, and so on. We will do until the last one. So it means you need to calculate for every distance. The requirement is minimum points equal to 4. Then you will check Here we have 2. Here we have 2. Here we have 3. We have 2. We have 1. We have 1, 2, 3, 4. Okay. And this is a cluster. We call this is cluster 1. This is only 2. We have 1, 2, 3, 4. Okay. We call this is a cluster. Let's say this is cluster 2. We have only 2 here. What about this? Oh, nothing. Here we have 1, 2, 3, 4. Okay, we can make cluster here. But if you look at the points, if you look at this point, 1, 2, 1.2, 2.5 is here. So the 1, 2.5, it is located here. So actually the group here is the same with the group here. And we can say this is the same cluster. So at the end, we can just set up that if it is less than the minimum points 4, so we have 2, so it is the border point. This one is also having 2, so it is the border point, border point, border point, border point. And then this is the cluster 1, because the 2.8, 4.5, it is the core point. Okay. So this is the core point, this is the core point, this is the core point, this is the core point. So the core point can create the cluster 1, and then here is another core point, because it can create cluster 2, and this is another core point. It can create, this is the same. This one and this one is the same. So we can conclude that cluster 1 is having 5 points like this one with 1 core point, and then the cluster 2 is this point, and we have the outlier. What is the outlier? The outlier is the point without neighborhood point. So you can see there is no point. There are no points in this regard. So we call this is outlier. So the conclusion, the outliers, we have 3 points. This is the outlier. Okay. So the DBSCAN, it is sensitive to the parameters. When you change slightly the parameters, then the result will be different. For example, this is the DBSCAN result for the DS1 with DS1 is the dataset 1. This is the dataset 1 with the minimum EPS, minimum PTS, minimum points at 4, and the EPS is 0.5. This is 0.5. And this one is 0.4. So you can see that the distance between the points affect the clustering results. If you can find a good EPS, you can have a good clustering. If you set the numbers is very low, maybe the result will not appear as you want. And let's see this another example with the dataset 2. we have the minimum points at 4, and the EPS is 5. This one is 5, and this one is 3.5, and this one is 3. So if you use a very low minimum points, with a very low EPS, then you cannot figure out the clusters clearly. But if you can select a good EPS, then you can find the shape of that cluster. There is another kind of clustering. They call it the CLARANS, but I do not explain about the CLARANS. If you want to check by yourself, yeah, you can check on the internet about the CLARANS. But what I want to show here is we can have like this data. So sometimes this kind of data appears, especially if you are in astronomy. If you want to see stars, so there will be some distance, and if you use the CLARANS, the result is something like this one. This is the stars. This is, maybe there are some data like this one. There might be some data. This is usually it can be happen in the Earth. From the satellite, you can see islands. So some islands in the Pacific oceans. You can see some data like this one. And if you want to clusters, let's say I want to see those data with the algorithm CLARANS, then this is the result. If you look with the database, with density base or DBSCAN, you can see the result like this one. So it's like, it's more clear how we can see the result based on the shape. Okay, that's about the density-based methods. So let's continue with the grid-based method. In the grid-based clustering method, we call this is grid. We are going to use the multi-resolution grid data structure. Grid, we call grid. It is something like, you can separate with some section. There are some interesting methods. I may just use only one. This is the STING. It is a statistical information grid. There's another method, we call it wave cluster. I will not explain this one. And there is another method, we call it click. So I'm going to explain the STING and the click. STING. It is a statistical information grid approach. If you look at the area, like for example in Seoul, okay, the big city, you can separate into gu, okay, Mapo-gu, Gangnam-gu or something. So the idea is the same like that one. We have the spatial area. We are going to divide it into the rectangular cells. If the earth or the city can be distinguished with the district like gu, but in this setup, we want to divide into rectangulars. We just want to make a kind of rectangular like this. There are several layers of cells corresponding to the different level of resolution. The first, we call it the first layer, and then the next layer we call it I-1 layer, and the last we call it the I layer. Each cell at a high level is partitioned into a number of smaller cells in the next lower level. So if I have one rectangular like this, so then in the next level we can have a different rectangular. So we can split into, let's say, 1, 2, 3, 4, 5, 6 rectangular. The statistical info of each cell is calculated and stored beforehand, and it is used to answer to queries. So sometimes we can have from the higher level to the lower level, or we can have the lower level to the higher level. Parameters of higher level cells can be easily calculated from the parameters of the lower cells. So let's say how many data, count, or what is the average, or what is the standard deviation, what is the minimum, what is the maximum. And we can also figure out the type of distribution, whether it is normal or it is uniform distribution, and etc. This method is usually a top-down approach to answer the spatial data queries, because this is a very early approach. So they say that it is the top-down approach, and they use the rectangular. It starts from a pre-selected layer and typically with a small number of cells. So if you have a very big cell like this one, maybe it is difficult. So you will just select a very small cell, maybe this cell, and then you can check with the top layer, and then you can find again in the top layer. For each cell in the current level, compute the confidence interval. So there is a way, there's a method to calculate the confidence interval, but let me just skip that one. So let's see with one example. So in this example, we have some data like N, M, S, minimum, maximum, and the distribution. N means the number of objects or points. So in the cell number 1, we have 100 data. In the cell number 2, we have 50 data. In the cell number 3, we have 60 data. In the cell number 4, we have 10 data. M, it means the mean of all values in the cell. So this is the mean or the average. So 20.1. This is the average, 19.7. This is the average, 21.0, and then this is the average, 20.5. S is the standard deviation. So this is the standard deviation. And then min is the minimum value. And then max is the maximum value. And we can also look at the distribution. The distribution is the type of distribution that the attribute value in the cell follows. So if we check with the statistical test, then it follows the normal distribution. It follows the normal distribution, but in this data, no. So there is no particular distribution of this data. So this is just an example from one data set. Now I would like to figure out what is the top what is the top level of this cell. Then we can just do the aggregation. How can we do the aggregation? Based on the n, we have 100 plus 50 plus 60 plus 10. So the top level, we have the total data is 220. And then we have the m. M is the average of the average in every cell. And this is the standard deviation. Okay, we got it from every standard deviation on every cell. And yeah, this is the minimum. So the minimum we have 4.5, 5.5, 3.87. So the most minimum is 3.8. And this is the maximum. So among the maximum, we select the maximum value, which is 40. And the distribution. The distribution, most of them are normal. Only 10 data is not normal. So we just mention distribution normal, and the 210 points whose distribution type is normal. So this kind of mechanism, we call it with the STIM, Statistical Information Approach. So for the analysis, we can remove the irrelevant cells for further consideration. Let's say if you think that the cell number 4 is not relevant, then you can remove that cell. When finished examining the current layer, we can proceed to the next lower level. So repeat this process until the bottom layer is reached. So we can have like one time from the top to the bottom, or from the bottom to the top. And yeah, some advantages of this one, it is query independent. It is easy to parallelize, and it is incremental update. And if we use this algorithm, it is linear, OK, where K is the number of grid cells at the lowest level. This algorithm is easy, but there is a disadvantage. All the cluster boundaries are either horizontal or vertical, and there is no diagonal boundary is detected. So we just have from top to bottom, or maybe we can say from the right to the left, or left to the right. But there is no possibility for diagonal. Diagonal means, yeah, if we top down is vertical, or this is horizontal, but there is no diagonal like this one. There is no diagonal to calculate with this thing algorithm. Okay, let me stop here. Let's have a break. I will continue after a bit.